here. And that's fine. Sorry, I'm still a relative newbie here on these things. So, okay. Give me 1 second. I got to get my notes back up here. Hey, sorry about that. All right, our next speaker is Dr. Bryan Vining. Dr. Vining is the Laboratory Director for Enthalpy Analytical Ultratrace in Wilmington, North Carolina. He is a 22-year veteran of the laboratory industry, starting his career as a product specialist and later working in various lab roles before joining Enthalpy Analytical LLC in 2016. Bryan graduated with a BA in chemistry from Huntingdon College before proceeding to get both an MBA and PhD from the University of North Carolina, Chapel Hill and Florida State University, respectively. His areas of expertise are in contaminant testing, including PFAS and persistent organic pollutants in environmental and food matrices, using isotope dilution mass spectrometry with HRMS, LCMSMS, and GCMS. Welcome, Dr. Vining, and would you please begin your presentation?
Right on. Okay, so interestingly enough, we heard a little bit already about short chain PFAS compounds, and really my entire talk is about that. So they, as indicated, are becoming of much higher interest in recent, really months, but years perhaps, relative to the more historically prominent legacy PFAS compounds. And even, you kind of have three phases where you had the legacy compounds that were of interest historically, then the so-called replacement compounds and their related entities. So this would be Gen X and the like. And then although some of these short chain PFAS compounds have been around for a very long time, they've really only become of interest fairly recently. And there are a number of reasons why they're interesting. As Heather mentioned, there's the fact that they are breakdown products from larger PFAS compounds. They're also fairly prominent in the waste streams of manufacturing facilities. And of course, they migrate. So that means that they're not just limited to where there may have been a manufacturing facility that either was or still is making use of PFAS compounds. And so as a consequence, there's a growing interest in being able to analyze these compounds. But there are a number of challenges in performing those analyses. So where does this fit in? Typically, we're looking for short chain PFAS compounds in non-potable water samples. It's not to say you couldn't try to look for them elsewhere, and I think they are going to be of increasing interest in air emissions, but at the moment, most of the interest has really been in non-potable water sources, particularly things like effluents from wastewater or manufacturing facilities. So, we've got a large number of capabilities, but we're really going to focus in on these ultra short chain entities, and we're going to talk about how that analysis gets done in a couple of cases where they've been really helpful for customers and may in fact be really useful for other folks out there. So we have been analyzing now for about 2.5 years, half dozen of these compounds. So those are the ones on the left of this slide. And you'll notice that we have TFA and PFPRA. So those are from Heather's talk as well as some additional compounds that are of interest for a variety of reasons. Most of these are related to manufacturing in some way, shape, or form. And we have been looking at those for quite some time, and we also have been really happy to find that CIL has produced a couple of labeled standards that fit in well with this for PFPRA and TFA, and I look forward to when they have more. Uh, and these are challenging relative to the legacy compounds in a number of ways. First of all, they're really prominent in the environment. We get some background issues that are even worse than what you normally have when you're trying to do PFAS analysis, and I'll talk about that a little bit more. And then, of course, their chemical properties are quite different in terms of polarity, size, so on. So you really cannot effectively get good separation for all the PFAS compounds from 1 carbon to 18 carbons. There's just really not a good way to do that. Not one single column chemistry that covers it all. So those are both a couple of challenges. We are going to be adding more analytes to this mix. We're actually working on that right now as I'm talking about this. And a couple of these are even trickier because they actually have 2 acid sites rather than just one. So they behave a little bit differently than the rest. And why that's an issue will be apparent in a moment. To address the fact that these are so much more polar than your typical long chain compound, you can't run this through a standard reverse phase column. TFA will shoot right through with no retention, and most of these will have little or even no retention as well. So you need a different approach in terms of the chromatography. We've come at that using the Raptor Polar column from Restek, and we are looking at some other possibilities as well. That was just the first one that came to our attention that would do the job we needed done. But that's not to say it's the only or even the best one. It's simply one that we had available, and it works pretty well for the 6 compounds that we have been analyzing for the last few years. So it's a simple 2.1 by 50 column. I'm not going to go through all the chromatographic conditions in gory detail, but you can see there what we're doing. And thus far, it's been a isocratic method with a gradient on it. And there's really 2 different ways you can go about doing the analysis in terms of the sample prep. You can either do a solid phase extraction, as is done for a lot of PFAS compounds, or you can do a direct inject preparation. And actually, the direct inject preparation has been the one that we have preferred historically. And the reason for that is that these compounds, or at least some of these compounds, behave problematically when you're going to do solid phase extraction. So, for example, TFA can cause some real problems with recovery. And we're still investigating exactly what's going on with that, but it depends a little bit on what phase you're using for your solid phase extraction, as well as the elution conditions. And then even if you get that to work out, you have another problem in that PFPRA is actually present in, it seems like, everything, just absolutely everything. And, those of us that are used to working with PFAS analysis are used to PFAS being in everything. But it's easy to kind of overstate how present PFAS are. It's hard to overstate it for PFPRA. It is really in absolutely everything. And so it's a real challenge when you're trying to do, say, solid phase extraction, because we can get, as you will see in a minute, clean blanks for PFPRA when we do direct inject analysis. We have yet to pull that off consistently with solid phase extraction. Sometimes we're there, sometimes we're not. So that's why we've leaned towards the direct inject analysis whenever possible. But sometimes The limits we've needed have required SPE, and then that's created its own host of problems. But we have a solution for that, which I'll talk about in just a sec. Uh, and then these are some mass spec parameters. Now, these are for the SciEx 7500, which is the instrument we've recently started using for this. And as you can see here, we're getting some pretty nice instrument blinks here, particularly when you see what the limits are. So we've got arrows where we would expect to see the compounds, the retention times that we're seeing in the standards. And as you can see, they're pretty clean. And TFA, we've got nothing. PFPRA, we've got nothing. So as I said, with the direct inject analysis, you've got pretty clean blanks, and that turns out to almost never be true for the SPE, at least for PFPRA, if not for all the other compounds. And then this is actually the lowest point on our calibration curve at the moment for this analysis on the SciEx 7500. Now, we've not actually pushed this yet quite as far as we probably can. It is a little bit of a work in progress, although we've got enough of a method to be able to do measurements, and we have done measurements. We actually just finished up a project with EPA not too long ago on this. One of the things we have seen is that with the polar Raptor column, at least the 2.1 by 50, we're starting to run into having insufficient coelution or separation rather, which is why we are looking at some other columns. But as I mentioned, one of the things that we did to address some of the issues with reporting limits that require SPE is we have now adopted much more sensitive instrumentation. So historically, we were in the near part per billion range for our reporting limits. If we were in part per trillion, it was very high. With this new instrumentation, and again, we probably are going to end up a little bit lower than these numbers. You now are into the tens of part per trillion, and it becomes much more practical to use that as the prep scheme, even when folks need fairly low reporting limits. Although I still am seeing requests for reporting limits as low as 10 part per trillion, which I'm not really sure is necessarily anything that's biologically relevant, but it's what folks are asking for. And for PFPRA, that's going to be an extremely difficult proposition because we really can't do SPE and get down to that kind of limit due to the background. In fact, the 35 part per trillion we're showing here is lower than the reporting limit that we offer for our solid phase extraction. And that's due to the fact that 35 part per trillion is roughly the background that we get when we do solid phase extraction. So just real quickly, I'm going to talk about a couple of ways we have used this technology to help out some customers. One of our sister companies, ECT2, is working on a water treatment pilot study, and they needed to be able to make adjustments pretty quickly. So one of the things we needed to be able to do is not only measure this wide array of compounds, but do so rather quickly. So here's where the direct inject analysis really helped us out, because we were able to put this method together that would analyze the compounds they needed and then some, and be able to also turn the data around very quickly because we're doing the direct inject analysis. Now, the one thing that they really would have liked to have had more is lower reporting limits. Now we're going to be able to offer that as well. Now, they were also looking at some legacy compounds, and obviously those had to be run on a different analysis. So to capture the full breadth of the compound list they were interested in, we would have to do 2 analyses for every sample. But we made that work, and we were able to do both with direct inject that got reporting limits sufficient for their purposes, because they were working on treatment, so they were typically starting out with pretty high level samples to begin with. So we didn't have to get to super low reporting limits. Now, a different case where we actually did need to get to pretty low limits is another customer of ours, an industrial client in North Carolina, who needed us to look at 3 smaller PFAS compounds that they also needed to have very low limits on. They had gotten a new permit from the state for their facility, and that permit had significantly lower limits than they had been having to meet. And they came to us because their internal lab told them that there's no way we can do that. So they asked us if we could, and because we had the SciEx 7500, we said, sure, we can do that. We can make this happen. And we prepared another direct inject method for them. And that was also critical because they were looking to get data in anywhere from 1 to 3 days. And we have actually had to turn data around for them in a day, which, even if we didn't have the background problems from SPE, turning around SPE in a day it's tough. It's doable, it's possible, but it's definitely not something that's done all the time. So the direct inject method really helped with that, but we were able to get to below 10 part per trillion. In fact, all of the compounds that they asked us to look at, we got to reporting limits of 5 part per trillion or less using the direct inject approach for the compounds that they were looking for. And we are very excited about where we're going to go with this method as we add more compounds to it, and hopefully add more labeled standards to it as well. Because whether we're doing direct inject or SPE, the ability to use the isotopically labeled standards to control for instrument variation is key to what we're doing in terms of providing the best accuracy and reproducibility that we can. And so with that, I will wrap up the talk here, give thanks to a bunch of folks on my team who have helped, as well as a couple over at ECT2, and I'll take any questions that you have.
All right. Thank you very much, Bryan. If you could stop sharing for a moment, that would be great. I have one question that has popped up. Have you considered using the online SPE method?
Sure, that is a consideration, and it's something that we may well look at. The problem we are likely to run into is the same one that we have with offline SPE, which is background. Now, we haven't investigated that, so we might get lucky and find that there is an online SPE column that does not have the same kind of background issues that we're seeing with the offline process. But as I say, we haven't looked at that yet. So, I don't know whether that's going to be a viable technique or not.
Okay, thanks. Yeah. And I'm going to take a minute. Thanks very much for the plug on the isotopically labeled standards. It's obviously something that we've known for a long time. That's why we do what we do. The use of the stable isotopes is great to allow you to get those lower detection levels and have accuracy down at those ranges. I'm just curious, are we maybe taking this too far, in your opinion? How low is low enough? I know the instruments are getting better, and I know analysts are able to get clean equipment and things like that. But is it low enough already, in your opinion, or should it keep going lower?
Well, that's a great question. And the answer is both yes and no, right? So in terms of the instrumentation, there's an argument to be made that you don't really need to be any more sensitive, right? Because, well, SPE will get you there. And that's true enough, right? There's no argument. And there are other benefits to solid phase extraction apart from the fact that it concentrates your analytes of interest such that the instrumentation can get to the reporting limits that are of concern. Now, whether the reporting limits that are of concern themselves are too low, well, that's a whole other ball of wax, and I'm not a toxicologist, so I'm going to stay out of that argument. But one thing I will point out in favor of at least a little bit more sensitivity is that when you do not have the concern about matrix interferences with a sample, direct inject offers a much less expensive and a much faster analysis than you're going to get with the solid phase extraction. And solid phase extraction is not a lossless procedure, right? And since you do not have, at least yet, a full suite of isotopically labeled compounds for every compound of interest, there is the potential for asymmetric loss between something that doesn't have an isotopic label and the isotopic label that ultimately ends up getting measured against, right? So in that respect, the direct inject analysis is also arguably a better approach. Now, the one place where the direct inject is not going to be better is where you've got a sample matrix problem that you can't dilute out that solid phase extraction would take out. The flip side of that argument is that solid phase extraction not only concentrates your analytes, but it also concentrates any interferences it doesn't remove. So there's never, it's never going to be an all one way or all another situation. Some samples are going to work better by direct inject and some are going to work better by SPE. So to the extent that we can get to the limits needed, according to those who come up with such limits, with instrumentation doing direct inject analysis, I think that's as far as we need to go. Does that mean we're going to stop there? I have no idea. I have my personal feeling is that probably the lower the instruments go, the limits are going to come along with them. But who knows?
Well, I guess that's good news for isotope manufacturers like us. But also, I kind of did that gratuitously to see if I could stir up some interest from other people to chime in on their opinions. So yeah, thanks for your answer. And by the way, one other gratuitous thing, we do have native and labeled MMF already in stock. So in case you're looking to get into those, I saw those on your new list. So.
Yeah, MMF is there, so I'll have to get that from you.
Great, appreciate it. All right.